All right. So, hey, welcome to another week of differential equations. Um, yeah, my plan today is um, pretty much pick up where we left off. And today we're actually going to start into second order differential equations. We've already kind of had a little bit of a preview of where they show up because, like, when we were talking about um, like the air resistance question, that led to a second derivative in terms of position, but we were able to turn it into a first order in terms of velocity. Well, can't always do that. So we'll start turning our attention to second order differential equations and see what we do with those. So that's my plan. But before we go there, I'll open up to you guys. Any questions about what we've been talking about? Any questions on the homework? Actually, that just reminds me real quick. I did move I want to say it's 4.3 section, the section on basically physics, the mechanics bit. I moved that one to next week. So just FYI. But anyway, questions, any homeworks we want to look at?
Could you go over problem 14 on 2.6?
I'm sure we can do that. 2.6, number 14. All right, and then Ralph, I see you asked for 4.2, number 18. I'll put that on the list. Any others?
If you have time, 17 as well on 2.6.
I will put that there. I think we can do that. Okay, well, let me go ahead and pull that stuff up and we'll take a look at them. So 2.6. All right, let me share my screen. All right, so here in 2.6, we're looking at numbers 14 and 17. So these just say find an integrating factor and use that to solve the given equation. And then 17 is similar, but a little bit different. So let's take a look at 14 first. So we got this guy right here. Let me go ahead and write that one down. And then we'll go to the whiteboard. So we got cosine x cosine y times dx plus sine x cosine y minus sine x sine y plus y dy. Okay, so let's jump to the whiteboard. Okay, so first thing we should probably do is just confirm that this is going to be one that's, or is one that's in exact form. So how do we do that? How do you check to see if it's exact?
Take the first partial that's attached to the dx with respect to y, and the second one that's attached to dy with respect to x.
Yep, and we just see if those are the same, right? Okay, so let's do that. If we look at f sub y, it's a cosine of x. Derivative of cosine y is a minus sine of y. We get negative cosine x sine y. And then if we come over here and we do a f sub x, okay, so we get derivative of sine is cosine of x times cosine of y. And this one, derivative of sine is also cosine, so minus cosine x sine y. All right, so there are those guys. Uh-oh, they're not equal. All right, well, what do we do then?
We can do my, so I guess in your writing, fy minus fx over f, I suppose. The one attached to dy, and
Okay,
do some algebra and see if there's only x's left.
okay, good. Yeah, so we want to look at the, I guess, yeah, I should probably go back to their notation, right? The my minus nx stuff. But we want to look at the difference of those and see if we can divide it by either m or n and get it so that it's only a function of one variable. Okay, so, sorry, I lost my window here. So let me, we call that guy M, this one N. Let me just redo those real quick. So this was my equals minus cosine of x sine y, and this is nx. So if we look at the difference of them, we're going to want to do one of two forms, right? We're either going to want to do my minus nx divided by which one? Which one do we divide by there?
N.
Right? So for the my minus nx, that one we actually divide by m. The other one is nx minus my divided by n. So let's see what we get for these guys. So my minus nx, if I subtract this, I get 2 minus 2 cosine of x sine of y minus cosine of x cosine of y. And we're going to divide that by cosine of x cosine of y. So let's see how that one plays out. So the cosine x cosine y, that all cancels over there. So we're going to get minus 1. Over here, the cosines cancel. We get minus 2 tangent of y minus 1. Okay, so let's just pause for a second. Is that good?
No,
No, why not?
there's two variables.
Oh, there aren't two variables anymore. It's just y, right? All of the x's ended up going away.
Then in that case, then yeah, it's good.
Yeah. Do we want that thing to be a function of x or a function of y?
Should be function of x.
Okay, so if we go back, let me actually find it here. Okay, I'm going to switch sharing here real quick. Let me go to the part in the book. Okay, so we'll come back here. So we're doing my minus nx divided by n right now. And it says if that's independent of y, then, okay, then we can do what we're doing. But this one's not independent of y. It very much depends on y. So you got to be kind of careful. Just because one of the variables goes away, it doesn't necessarily mean that the one you needed to go away went away. So unfortunately, that one's not going to work for us. So let's reverse it. And let's go take a look at those. Okay, so we'll hop back to the whiteboard. And let's do this one again. So now we'll do nx minus my. So cosine x, cosine y. And then when I subtract the my, those pieces go away. And then that's all divided by sine x cosine y minus sine x sine y plus y. Okay, so how do we feel about that one? That one we need to make it only in terms of y. So does anybody see a way to get rid of the x's?
I don't see a way.
Yeah, this one, we're pretty much toast. It's not going to work. Okay, so this is where we have to pull a little bit of a trick. Okay, so if you kind of go back and you look at the derivation of how this all played out, when we looked at that special case, well, it was a special case of another circumstance, and what we really need, and this is what came about from the derivation when we did this, oh my God, forever ago. I don't even remember when this was anymore. Basically, what we needed was my minus nx to be something of this form. And what we were doing before is we were like, when we got the ones that were exact, this was such, like if you look at this, for example, right, when you divide out the, say the n, we have some function of x times n. Well, that was that function, right? And so anyway, what we were looking at was a special case, but this is what we really want to do. We want to see if we can break it down so that there is some function of x times the n plus some function of y times the m. And this is the trick when it doesn't quite pan out the way you want. So here's what we would need. We need p of x times sine x cosine y minus sine x sine y plus y minus some function of y times cosine x cosine y such that that equals the difference in the my and the nx's. So that the top of this over here. And so let's just kind of start building this. So in terms of the cosine x and cosine y, there's just this one term that has a minus cosine x and cosine y. So that tells me that q of x, or sorry, q of y has to have a 1 in it. So that's going to give me this. Okay, and then if we look at the minus 2 cosine x sine y, we look at this piece, that tells us that p of x has to have in it a minus 2 to give me this piece. Okay, now that's clearly not going to work though. We just use these because the minus 2 also leads to a 2 sine x sine y and a minus 2y. So we have to get rid of those. And so the trick with that, trick to get rid of those suckers, is to think about what we would put in here to cancel those out. So we're going to have to add in extra pieces into this queue to counteract those other pieces. Okay, so this is basically like a system of equations kind of deal, but a system of equations, but without constant coefficients. So I'm kind of feeling like I made a mistake somewhere though. Let me just go back and double check. I'm first looking down to see that I wrote it down right. So Ralph, when you say you think I got the equations wrong, which equations? I'm going back, go back to look at the, make sure I have my question right. So my minus nx divided by n. Hold on a second here. I was double checking that I wrote this down right. Boom, boom, boom. Okay. So give me a second here. I'm on a different screen. Okay, so my, derivative cosine is a negative sign. So I feel pretty good about that. Nx, cosine x, cosine y, minus cosine x sine y, and that piece goes away. My minus nx is that. Oh, you're saying I'm dividing by the wrong things?
See, here's the thing about that though, is in the book it shows it both ways, and it's getting on my nerves. It does it sometimes in the examples in the book divided by m or n, and I don't know why.
Well, it's okay. So you're dividing the one, you're dividing by the one versus the other to see if you're only in terms of y or x. So let me switch my share. Let's go back here. Right, because here was how we built the integrating factor. So we need to have my minus nx divided by n as a function of only x, right? So independent of y. And then the other one is nx minus my divided by m has to be independent of x, so meaning a function of only y. Okay, so I should have my minus nx divided by n. All right, good catch on that. I don't like the m and n. It's not how I learned it, which is why I get that mixed up sometimes. Okay, well, if we do it this way, then you should see that this is going to work out kind of nicely. Whoops. This is one of those days, guys. One of those days. Okay, so this thing is ugly as all get out, right? Clearly not just in terms of one variable, but the other one, this one's going to be good because the cosines cancel and we get minus cotangent of y, which is what we wanted. We wanted something that was only in terms of y, was independent of x. And now we can get the integrating factor. The integrating factor is going to be e to the integral of this thing. So we have our mu is equal to e to the integral of negative cotangent of y. So what's the integral of cotangent?
The natural log of sine of x.
So hold on. So Ralph, you say it's not negative cotangent of y? Oh, God. Yes. I divided by my instead of by m. That's m. Which makes this 1. Okay, well, good news is that's really easy to integrate. Right. Oh, except I swear to God. Except I'm not integrating with respect to t this time. What am I integrating with respect to?
Y.
Because it can't be t. No, sorry, I get it. Why? Who's on first? Yeah. Okay, so this is independent of x, right? So it's only in terms of y, so we're integrating that with respect to y. Oh, good Lord. Okay, so we integrate that thing with respect to y. So that gives us e to the y, which then that's our integrating factor. So we go ahead and we multiply that into here. And now we should be good to go. Should is the operative word. Because at this point, I feel like just cutting our losses and saying class is over, man. All right. So anyway, now that we're here, remember what we have to do. We want to integrate the first piece with respect to x, because we're looking for the function whose gradient is what's given here. So we're going to integrate e to the y cosine of x cosine of y with respect to x. So that's going to give us e to the y sine x cosine y. Because all that y stuff is constant. And then, of course, we can have extra stuff that's only in terms of y. All right, and then we're going to integrate the other piece. With respect to y. And what that's going to give us is that same e to the y sine x cosine y, because its derivative is these two pieces if you use the product rule. So just it is. And then we're going to have to integrate the y e to the y, which I think gives us y e to the y minus e to the y. So now that we have that, we can put those things together. So we're going to get e to the y sine x cosine y plus y e to the y minus e to the y equals constant. All right, so I apologize for sending us on the wrong track with our M's and N's backwards. That's what I get for not looking at the book's notation and just trying to do it my way. All right, so the trick with these obviously is when they're not the same, you create your integrating factor by doing this little trick. So I would ask if that helped for 14, but I think it probably just confused you more.
No, it did help. I found my mistake.
Okay. Hopefully it wasn't, or hopefully it was one of the many that I made along the way. Oh my goodness. All right. So that was number 14. Let's go look at number 17. Ah. Okay, so number 17. So in this one, it says find an integrating factor of the form P of X times Q of Y and solve the given equation. All right, well, let me write this down again. Y times 1 plus 5 log X, 4X log X, dy. Okay. So let's come here, clear out all that nonsense, and let's start anew. All right, so we had y times 1 plus 5 natural log of x dx plus 4x natural log of x dy. Well, let's name these guys again. See if we can make this work. Okay, so my is 1 plus 5 log x. And x is going to be 4 log x plus 4. So just did the product rule on that guy. Okay, so let's look at the two different possibilities, my minus nx over n. So if I subtract those, I get natural log of x minus 3 divided by 4x natural log of x. So before I move forward, I'm going to ask Ralph, did I do that right? Or anyone else can chime in there, but
Yeah, I'm in agreement with you.
so evidently my computer wanted to kick me off mid problem. Yeah. And my whiteboard. No, of course my whiteboard went away. So how far did we get before I was quit being shown?
We had just found my minus nx over n,
Okay.
which was natural log of x minus 3 over 4x natural log of x.
Okay. All right. Well then, let me get back to that. All right. Give me a second here. Everything is all out of whack. Let's try this again. Okay, whiteboard, share. All right, you guys see the whiteboard, I hope.
Yeah.
Okay, so real quick. Okay, so we were there and we had found the my minus nx over n was natural log of x, was it minus 3? Is that right? That's a legit question because I don't remember.
Yeah, that's
Yeah.
what I have, except it's
Okay.
over. Yeah.
Yeah, we're good.
Yeah.
Okay, so then nx minus my, well, that should be 3 minus natural log of x, but now divided by 1 plus 5 natural log of x. So again, I'm looking for a confirmation. Is that right? The book wants me to do it a different way. At this point, I don't care. Because this is still going to work out. This is still going to totally work out. And I think we can actually craft it so that we are doing what the book wants us to do. So because this is good news, right? You notice that both of those are only in terms of x, which means we're going to be able to use one of them, right? We've got the one that's independent of y. So the question is, which one is it? which one of these did we need to be independent of y, to be only x's?
The first one.
The first one. Okay, so we're going to run with this one. So we're going to get our mu equals e to the integral of natural log of x minus 3 over 4x natural log of x dx. All right, so I'm sure that's some really ugly, horrible, whatever. But if we go back to what the book said it wanted, let me pull that back up here, where it said find an integrating factor of the form p of x times q of y. Well, for us, this is going to be p of x, and q of y is going to be 1. So that when I multiply those things together, I've got my integrating factor. So the whole like p of x times q of y, that can be used for forms that are not nice like this, that don't get it so that we're only in terms of the one variable. And so when that happens, that's where you can split it apart, kind of like what I was showing you for the other one when I did the mistake and we had the horrible looking thing that we were splitting apart. But in this case, this is just a special case of that, where the other function is equal to 1. When it comes time to integrate this, I would split it into 2 pieces. Because like that first part, the natural logs will cancel. So what you're integrating there is just 1 over 4x for that first piece. And then the other one is 3/4 times 1 over x log x. But your calculator can handle that. It'll get you whatever your integrals are. And then we can take e to those powers and all that. Like this part's gonna be nice because that's just gonna give you an x to the 4th. You're gonna get 1/4 natural log of x, bring the 1/4 in, the natural log and the e cancels. The other part, I don't know what that's gonna give us off the top of my head. But anyway, from here, it's just a couple more steps and you should be good. So Ralph, you said the book wants you to do a different way. What did you do? Or did you even try this one? Okay, so you did it the way that I was setting up the first time. Because that works too. And like I said, I mean, that's the general case where this is a real specific scenario where either your P or Q is basically non-existent. So
Why is q of y 1?
because they said we wanted to find an integrating factor that was in the form p of x times q of y. And this thing's going to be only x, which tells me my y piece has to equal 1.
So if there were y values in that, it would be different.
Correct.
Got it.
Correct. Yeah, and if you look at what Ralph put in the chat box, the whole, you've got your my minus nx equals p of x times n minus q of y times m. These big P and Q are the integrals of these. And in this situation, notice that the my minus nx over n is only in terms of x, which would suggest that q of y equals 0, right? Well, what do you get when you integrate 0? You get a constant,
That makes sense.
right? And so then what we're going to have to do is we're going to have to integrate this little p to find our big P. Well, that's that integral thing to get to there. Anyway, just it's a specific case of the general process.
Just to make sure, if we cannot find little p and little q, can we still use? Can we just still find big P and big Q, or that doesn't work?
So no, that won't, like, there are equations that this method will not work on.
Mm-hmm.
So there are going to be times where you can't find the little p and q's. So you can't find the big P and big Q. Sometimes you don't actually have to find the little ones. You can find the big ones by doing some like system of equations deal. But there are going to be times where those are just not, you can't find an integrating factor that works. So
So that the other method of that system of equation, that can be faster. That's why we can use it, or it's just because it doesn't have anything different than the other ones.
well, sometimes it works where this one doesn't, because if there had been a y anywhere in this first one, we would have been sunk. We wouldn't have been able to do this process. And that's where finding an integrating factor of this form is what you want to do.
Okay. So
Not that it's
failed-
faster necessarily, just that it's possible.
Okay. Yeah, that's a main question. Just
Okay.
to make sure that if one doesn't work, we go to the other.
Yeah. Anyway, does that make more sense? At least answer that a bit.
Yes, thank you.
Yeah. Okay, cool. All right, now I'm nervous. Let's go take a look at number 18 from 4.2. But that should be an application problem, so. Okay, so 18, control mechanisms allow fluid to flow into a tank at a rate proportional to the volume of fluid and to flow out at a rate proportional to V squared. All right, suppose V of 0 equals V naught, and the constants of proportionality are A and B respectively. So A is going to be for the inflow, B is for the outflow. So we want to find V of t. So we want to find a function for the volume in the tank and then find the limit as t goes to infinity. All right, so we're kind of changing gears here a bit in that we need to create an equation and then try to solve it. We'll try to figure out what technique is going to work for us in that case. But let's see what we can do here. So I'm going to clear all this stuff out, and let's start by drawing the picture. So here's our tank. We got stuff flowing in. I got stuff flowing out. Okay, so we were told that the change in the volume, its input is proportional to the volume, and it's being removed proportional to V squared. We also know that V of 0 is equal to V naught. So there's our initial condition. All right, so how do you guys feel about this equation? Does that make sense? It's
Yeah.
the same as we always do. It's in minus out. And this is just what they told us, proportional to the volume coming in and proportional to the volume squared going out. Okay, so A and B are just numbers of some unknown. So let's go ahead and solve this thing. So what method do you want to use? Or maybe the question should be, what methods can we use? What are our options at this point?
Thinking Bernoulli.
Okay. So is it Bernoulli? What did we need for Bernoulli? This would have been from like 2.3 maybe?
We need v prime, or I guess, yeah, y prime plus a p of x times y equals some function of x times y to the r.
Okay.
And yeah, I think we might have that.
Okay, so the y's now really need to be v's, right? If we go back to the Bernoulli idea. So they need to be v's, but we definitely have equaling some multiple of v to the r, right? And we just need to make sure that we don't have that r, that exponent, as a 0 or a 1, and it's not in this case, it's a 2. So this one's definitely Bernoulli. All right, so we could use the Bernoulli method. What else could we do with it?
It's separable.
It is separable. So let's put our choices here. So Bernoulli. It is separable, right? Because it's all in terms of E. We can just divide that over. And then that guy's separable. Do you recognize any other possibilities here? It's definitely not linear first order because of the v squared. So we can rule that out. It doesn't look like homogeneous in terms of the new homogeneous because we don't have t's in here, so we can't write it as v over t's. Right, so that one's gone. Yeah, I really think that's about the extent. So the question is, which way do we want to do it? Or should we do it both ways for the practice? Let's do that. Let's do it both ways for the practice. And we'll see that we get the same thing either way. But we'll start with separable because that's probably the one that you guys remember better. So we can write that as v prime over av minus bv squared equals 1. So we're going to need to integrate this. We need to think of this as partial fractions. So I'll make it a v and an a minus bv. So we're going to need a over v plus big B over a minus bv. So that's big A times a minus bv plus big BV. And that's going to have to equal 1. So if we let V equal 0, then big A is 1 over little a. If we let big V equal A over B, then that thing cancels, and that gives us that B is equal to B over A. So that means that we're integrating. Let me pull out the 1 over A. We're going to get 1 over V plus little b over A minus BV. That's 1 over A times natural log of V minus the natural log of A minus BV. So at this point, we've got 1 over A times the natural log of V over A minus BV equals T plus C. So V over A minus BV is equal to C e to the AT. There's a new C that's actually e to the old C times A. So then we get AC e to the AT minus BC V e to the AT which I think brings us here. I'm trusting my algebra, though at this point, with how today is going, I probably should not. And we're left to figure out C. Now, I want to show you a trick. This actually came up on one of the homework sets where you had a form like this, where you had the C's on top and bottom. Check this out. This is kind of fun. What I'm actually going to do is divide everything by C. And what that does, obviously at the top is just A e to the AT, and down here I've got a B e to the AT. But since that C was an arbitrary constant, 1 over C is also an arbitrary constant. So in essence, what you do is you make it so that you go from having 2, having that arbitrary constant show up in 2 places, to having it just in 1. So this is a fun little trick, and it's actually really useful, but you do need to realize that what we just said, though, was that C does not equal 0. Because if C is equal to 0, I can't do that. But if C is equal to 0, that just tells me that V is equal to 0. So as long as I'm not in that situation where my volume is always at 0, this is going to work. Anyway, let's get our initial condition then. Use our initial condition to find C. So let me change colors over here. So we're going to have V naught equals A over C plus B, because the e to the ATs become 1s. So C is going to equal A over V naught minus B. So we put that back in. And we're now at V equals A e to the AT over A over V naught minus B plus B e to the AT. And yeah, there are ways that we can make that nicer. But for right now, I don't care. Okay, but while we're here, since we've already got our solution by doing it separable, let's look at what happens for the limiting value. Because remember, there were two parts to this. The first part was find an equation for your volume. So that's what it's going to look like as time goes on. Again, assuming that the initial volume is not zero, because otherwise that's a problem. So there has to be water in the tank to start. But then what happens to this as t goes to infinity?
It's going to equal 1, right?
It's actually not going to equal 1. But you're thinking the right thing. You probably divided out the e to the AT, right?
Well, I was just thinking, like, if you plug in infinity for both t's, both numerator and denominator are going to go towards infinity.
Okay, but if you get infinity over infinity, then you have to use L'Hopital's rule.
Oh, yeah.
Because that's indeterminate form. It could be anything.
Mm-hmm.
But think about this. If you divide everything by e to the AT, you're going to get an A on top. This piece is going to be a B. And then the other portion, this chunk, is going to be divided by e to the AT. So that bit that I put in the pink parentheses, when you divide that by infinity, that's going to drop off. So all you're left with is A over B. So that thing, if you take the limit as t goes to infinity, you get A over B. Or do L'Hopital's rule. That's fine too. That'll get to that. But as time goes on, we're going to end up with A over B. All right, so we got our answer. And we got it by doing it the separable way. But let me show you that Bernoulli is going to work as well. Oh, actually, real quick. Let me show you how we could have figured out the limit without even finding the answer. You guys remember how we found terminal velocity given the differential equation? That's a legit question.
It was so long ago.
I know Friday, a lot has happened since Friday.
We pretended that our derivative was with respect to velocity.
Well, that's how we solved the equation. But when we just wanted to find terminal velocity, we actually looked for where does v prime equal 0? So that was an equilibrium state. So we can do the same thing here. And you go, okay, so what are the equilibrium states for this? Well, if I factor out the v, I get this, and we get either v equals 0 or a minus b v equals 0, which is v equals a over b. And so these are your equilibrium states. If there's no water in the tank, it will stay no water in the tank. However much water gets put in is going to be removed. But there's also an equilibrium at A divided by B. And that's what's going to happen as we go towards infinity. We're going to approach that much water in the tank. again, depending on what the proportionality constants are. Anyway, there are shortcuts. There are always shortcuts to things, and this is one of the big ones. If you want to know what's going on, like limiting values, equilibrium values, just take your derivative and set it equals 0 and see what it says. All right, so that was the, just realize that it's separable and do it. Now let's do it with Bernoulli. And I'm gonna leave our answer there in the box just so that we can compare it to that. Okay, so let's try this now the Bernoulli way. All right, so first thing we should do for the Bernoulli is let's get it into the right form. So we want the linear piece over here, and then the part with the other power on this side. And I will try to use the notation of the book, but I don't remember exactly what they say. I think we're going to go with r is equal to 2, which is the exponent on that piece. And then I think they call them P and F. Does that sound right? That P of X would be negative A, and F of X was negative B. So those are just the multiples on the linear piece and the other one with the power. Okay, so what do we have to do for Bernoulli?
I'm thinking solved and homogeneous.
Okay, yep, we definitely start there. So we're going to find a y1 that was a solution to the homogeneous. Let me go back to orange here. So if we look at just the v prime minus av equals 0, that's going to give us a e to the at. Right, e to the integral of negative p, so negative a. So that's going to give us e to the at, and it should not be a prime, it should be a subscript. Okay, cool. Then what do we do?
We take the integral of f of x over y1 times y1. Well, it's y1 minus r in the exponent, I remember, times
Okay. You're really close. You're really close. So we're going to have on the left-hand side of the equation, we're going to get a u prime over u to the r. So we're going to get, we're trying to find a u, an integrating factor, but we're going to get u prime over u to the r. And that's going to equal f of x, so minus b, times our y1, so e to the at. And then we raise that to the r minus 1. So that's going to be the 2 minus 1. So that's in general what you do. You always do u prime over u to the r equals f of x times y1 to the r minus 1. All right, and now this we're going to integrate. All right, well, 1 over u squared is going to give us a minus 1 over u. Over here, e to the at to the first is just e to the at. So we get minus b over a, e to the at, plus c. So we'll get rid of the signs, and then we solve it for u by flipping it over. So it's going to be 1 over b over a, e to the at, plus c. I know that it multiplying the negative makes it a minus c, but a negative arbitrary constant is the same as a regular arbitrary constant. So that's our integrating factor, which means we want to multiply that by the y1. And when we do that, that gives us v equals e to the at times all of this. And if you multiply top and bottom by a to get rid of the fraction on the inside, this becomes a e to the at over b e to the at plus an arbitrary constant, which was exactly what we found. I mean, if you look, right? I mean, that's exactly that form. We're still going to get the same c either way. All right, so the moral of the story on this one is you could actually solve it either way. We tend to reserve doing the Bernoulli stuff if it's not separable to start, because Bernoulli is a way to make it separable if it's not already separable. And the key to that is if you look at the P and the F, these things were constants. And because it's constant, they're constants, this is already separable. Bernoulli is especially useful if this stuff has the other variable and you can't separate it to begin with. But if you see it's Bernoulli and you want to go with that method, it will still work. And I mean, I don't know, it actually was probably a little bit faster in terms of actually getting to the solution, but it required remembering the techniques for Bernoulli. And that's definitely a little bit more challenging than just separating to start with. Anyway. So how are we feeling about number 18 here? Is that better? I think it was Ralph. I think you're the one who asked about this, so we're good. Okay. Whew. So there you go. There's an application. Now I don't know when you would ever have a tank that's being filled at a rate proportional to its volume and being emptied at a rate proportional to the square of its volume. But if you ever run into that situation, you now can solve it. And think about that too, that the long-term amount of water in there actually was only dependent upon those two constants of proportionality. That should kind of make sense too, because that's really what's driving how much is coming in versus how much is going out. And so the fact that the end result depends on those two shouldn't be super shocking. I think it's kind of nice that it's just a simple ratio of the two, but that's just because of the structure of the problem. So anyway. All right. So good questions on the homework. And again, don't forget that stuff's due midnight tonight. And I think only through 4.2, right? Anyway. Okay, so a couple of things that I wanted to share that I forgot to mention. We're gonna skip section 4.4. We're actually not gonna do 4.4. I was looking at it and I don't think we really want to do that. I think it's probably more important for us to move into chapter 5. So just so you guys know, I'm gonna remove that homework. So it won't be there. You don't have to worry about that. But we're gonna move into chapter 5. We don't have a lot of time still remaining, but I do want to kind of dive into it and start talking a bit about it. And chapter 5 is all about second order differential equations. All right. So what our plan is now is working on techniques for how to solve things that have second derivatives. And I'm just going to stay down here. I'm not going to turn on the other camera. We'll just do it down here. So let me give you sort of a rationale for why we care about the second order. Like, when are we going to see these pop up? And I mentioned last time, or I mentioned earlier, that we did kind of see one last time when we were looking at mechanics, right? Remember when we were doing the free fall? And so we had gravity and we had friction. And so we went to the good old Newton's first law or second law. So we had the total forces, well, it was gravity minus the drag. And so gravity was just good old mg. Drag, we said it was proportional to velocity or proportional to velocity squared or whatever. And then for F, that was just mass times acceleration. And so we were able to turn this into a single or a first order by recognizing the fact that A is equal to V prime. So that was cool. It made it first order in terms of velocity. We could solve that. And then if we want a position, we could just integrate again. But suppose that we were to put in some other force that wasn't just dependent on velocity. All right, and so here's how we're just going to change this. Instead of having something that's just doing free fall, let's instead put this thing on a spring.
I
Okay.
thought for sure you were going to do rotational.
Well, we can do rotational and it'll lead to similar things. But I think spring's a little bit easier for everybody to see, especially for those of you who've not had physics. But here's what we're going to do. We're going to pull this thing down just a little bit. So we're going to lengthen out the spring. And then we're going to let it go. Okay, so we just pulled it down a bit. So there's some tension on it from the spring, and we're going to let it go. So even if you've never taken physics, just from your experience with the world, you know what's going to happen. This is going to start going up, right? And then it's going to get to some point where it reaches the top, and then it's going to come down. And then it's going to go up, and then it's going to come down, and it's just going to bounce back and forth, up and down, up and down, up and down. Now, in the absence of friction, in the absence of air resistance, this thing would just keep oscillating back and forth between the top and the bottom. But in the real world, we know that doesn't happen. Because what is this going to do eventually if you were to actually just do this experiment? What are you going to see happen with that weight that you pulled down?
It's going to slow down. It's not going to have as much of an apex of height.
Yeah, it's going to keep going up and down, but that up and down is going to get shorter and shorter until eventually it stops and it's going to be back in the middle. But if you were to draw a graph of, say, its height versus time, it's going to look sinusoidal, but those heights are going to get smaller and smaller, right? Okay, well, let's set up a force diagram on this thing. Okay, so let's do a force diagram on this weight that we're pulling down. So here's our weight. And let's start putting on forces. So there's going to be gravity. There's also going to be the spring that's pulling it up. Right, so even if there weren't air resistance, and this was it, we would still have this situation where we got gravity pulling it down and then the spring pulling it upward. Okay, but as it moves, there's also going to be some drag. Which direction is the drag going to point here?
Downward?
So as soon as I let it go, yeah, drag is actually pushing down because it's in the opposite direction of travel, right? So as this mass is moving upward, drag is actually pulling it down. We never talked about this either when we were doing just simple air resistance stuff. We always, had the ball just dropping, the object dropping. Well, if you were to take, say, a ball and throw it in the air, until it reaches its highest point, the drag is actually pulling down in the same direction as gravity. So it changes the formula just a little bit, changes the sign on the drag piece. In terms of solving, it's minimal difference, right? But it does lead to a different solution. Anyway, let's set this thing up then using forces. So in this case, we're going to have the force is going to equal, well, we got gravity going down, so mg pointing down. The drag is now pointing down, so we'll do kv. And then we're going to subtract the spring force. So I'm going to write you just real quick. F spring. Okay, so Newton's second law makes this ma. Well, that's just still mg, this is still kv. But now in terms of the spring force, do you guys remember how to calculate the spring force for you that took physics?
It was K something, kg.
Okay, good. It was K something, not G.
Yeah, kx. Or
Okay, so yeah, Ralph just put in, so it's minus kx, where K is the spring constant. So, how stiff the spring is. But the spring force was dependent upon position. Okay, well, now if you look at this differential equation, it's still a differential equation. Again, acceleration, that's an x double prime. Velocity is an x prime. Uh-oh. Hold on, I've got two k's. I don't want two k's. We'll use k for the spring, and we'll use, how about gamma for our velocity coefficient. And this one is second order. And in fact, it's linear second order. It's non-homogeneous because there's mg. But this one, there's no way that we can do this without creating a second order differential equation. Now you might be going, all right, let's eliminate the drag. Let's get rid of the drag because that clearly must be the problem, right? Well, if there were no drag, this piece goes away, right? That's still linear second order. So in the quote unquote real world, you run into second order differential equations pretty much anytime you're looking at kinematics. Anytime you're looking at forces, because force gives you acceleration, which is a second derivative. And as long as anything else in the problem has to deal with your position, with your x, that's going to lead to second order. So if nothing else, you should be totally on board with the, all right, yeah, we definitely need to know how to do second orders because second orders are going to matter in terms of application. Okay, so we were able to get away with it using first order stuff because everything was only in terms of v. And in fact, as long as all of your forces are only dependent upon the velocity, you can use first order techniques to solve for velocity and then integrate to get position. But if anything is dependent upon the position itself, any forces are dependent on the position, yeah, nah, now it's second order. Okay, so linear second order are always going to be able to be written in this way. Oh my God. What is up with me today? I even got good sleep and everything. All right, so linear second order, we'll go back to the y's and things that we're kind of used to. We're going to go with this as our kind of third form for linear second order. It's really the same kind of ideas we had before, because remember before we had y prime plus p of x times y equals f of x. Now we're just adding in one more piece, because if we've got a second derivative, we can also have a first derivative and then a constant part. Okay, so this is what it means to be linear second order. In terms of homogeneous or non-homogeneous, same deal. If f of x equals 0, we call this homogeneous. And this is back to the original definition of homogeneous, not that minor foray we had into the other type that could be written as functions of y over x. Okay, so we're going to do what we did with the linear first order, which is start with homogeneous. Okay, we're going to just start with what about these ones that are equal to 0? How are we going to find their solutions? Okay, well, let's look at that real quick. Not in terms of how we're going to find the solution, but let's just talk a little bit about the theory and what we should expect to happen in terms of solutions existing and all that. All right, so suppose that we have this and we even have some sort of an initial value problem. Oh, let me maybe talk about that real quick. For initial value problems, now you're going to need to know two things. When they were first order, we only needed one piece of information, right? You probably remember we only needed like y of 0 equals 5 or something like that. But now we're going to need two things, and it's usually, okay, but the important is usually, not always, but it's usually we're going to have y of, let's just say, x naught equals a number. And we're also going to have y prime of x naught equals a number. So that's usually what happens, is that we know the function and its derivative at the same point. It's not always the case, or not always what we need. We could know the function at 2 different locations and that'd be all right. Or any other kind of combination, but it's usually this. We usually know what the function's value is and how it's changing at a specific point. Okay, so suppose that we've got an initial value problem like this. It turns out that there's a really easy way to see if you have unique solutions. All right, and so this is a theorem for you. We're not going to prove it, but at least not today, we're not going to prove it. But if P of x and Q of x are continuous on an open interval that contains your initial value point, then the initial value problem has a unique solution. So if you go back and you look at what we needed for unique solutions for linear first order, it was actually very similar. We just needed that Q of x to be continuous because there was no P, but we need that Q. I guess we called it P and not Q. But anyway, the function that was on Y needed to be continuous. Well, now we need both of these to be continuous. But if they're both continuous, then you are guaranteed to have a unique solution. All right, so if your initial value is such that it equals 0, your unique solution is going to be 0 because there's still a trivial solution of y equals 0. But we're going to be in search of the non-trivial solution. All right, so let's just start here. Suppose we have one of these with just constant coefficients, with constant functions. So like the P and the Q, those things are constant. So how about this guy, for example? Let's say we were looking at, say, y double prime minus 3y prime plus 2y equals 0. Let's just start with what kind of function could be a solution here. What kind of function is going to be such that if we take its derivative and we take its second derivative, and then we just kind of like add and subtract and all that, what kind of functions might work in this sort of situation?
Polynomials?
Okay, so let's think about polynomials. Why do you think polynomials, Bradley? What about them makes you like them here?
When you take, first or second derivatives and powers of polynomials, they decrease.
Okay.
And I'm sure if you, plugged in initial value, you could get numbers that work.
Okay. So let me maybe paraphrase a little bit or put it into terms of something that I think is what you're thinking, but not what you said, is that when you take derivatives of polynomials, you get other polynomials. And so when you combine polynomials, it's possible to get 0.
Exactly.
Okay. Yeah. I'm just, I'm the Bradley whisperer, right? I'll just translate here.
I'm thinking sine or cosine probably.
Okay, so Victor just throws in sine and cosine and kind of the same deal, right? Like, let's say we've got a function that's made of sines and cosines. When you differentiate, that's going to give you sines and cosines. And again, if you differentiate, it's going to give you more sines and cosines. So those kinds of things might be able to cancel out. Right? As opposed to, like, let's say you had a natural log. If your function's a natural log, its derivative is now a rational function. And there's no way you're going to be able to combine a log and a rational function to get rid of them, right? So we know that natural log, for example, would be a horrible choice. But I do like sine and cosine. There's another really good function that could work here.
Functions of base E.
Yeah, how about an exponential function? Because we've seen derivatives of exponential functions are more exponential functions, which then could cancel. And so that's kind of the thought process here. And in fact, that's a thought process with any kind of differential equation, is to actually look at the form and go, okay, what kind of stuff, if I were to plug them in here, might actually cause these things to go away, right? Like, okay, so check out this one that I just drew right there. Let's try, for example, e to the x. Let's just say y was equal to e to the x. So then y prime is e to the x, y double prime is e to the x. I plug up, I get e to the x, e to the x's plus 2 e to the x's. Hey, check it out. There is a solution to that differential equation. Awesome. Right? So that one clearly shows that e to the x is going to work. So then you go, well, what about, say, like sine of x? All right, well, if we tried sine of x, let me clear a little space here. Oh, by the way, now that I'm erasing it, we know for sure there's a solution here to any initial value problem because p and q are both continuous. They're just constants, right? Anyway, but like, what if we said, okay, let's try, sine of x. So y prime is cosine, y double prime is minus sine. You plug that in, you get minus sine of x minus 3 cosine of x plus 2 sine of x. And you go, oh, yeah, not equal 0. So that one doesn't work. But it definitely has the potential to, right? It's not really hard to create a second order differential equation that does that. Like, what if we tried y double prime plus y equals 0? And we do that with sine. So erase this real quick. But clearly you can see if you take y double prime and you add it to y, you get 0. So this is one where sine of x is a solution, but e to the x wouldn't work, right? You plug those in, you get e to the x plus e to the x, which is not 0. So we are definitely looking for functions whose derivatives, second derivatives and all that, are the same kind of form as the original function, so that when we add them together, they're going to be able to cancel out. Okay, so in general, with these things, especially those that have the constant functions, where p and q are constant, we're going to see this. You're going to see lots of forms of exponentials and lots of forms of the trig, sine and the cosine, with these type. Okay, but how to solve them, we're going to save that, start doing that next time. All right. But we'll talk a little bit more about the theory behind them. And for those of you who like seeing the linear algebra, I'm specifically looking at you, Victor. You're going to really like next time because you're going to go, oh my God, this is just linear algebra all over again.
I have a question for you, but what you just
Sure.
said kind of alluded to the answer. I was going to ask, suppose you have one of these and I find functions that work and then you find different functions that work. Who's correct? And then you just said that, and now I'm like, oh, there's going to be a basis of them.
There is. Yeah, what we're going to see, I mean, that's all I had to say, right? Linear algebra, and you're like, ooh, basis. No, what you're going to see is that, yeah, there are going to be what we call a fundamental set of functions, basis. And all solutions are going to be linear combinations of that fundamental set. And so if I go and I find a solution and then you go and find another solution, they're actually going to be the same in terms of, a basis for the space or a set of fundamental solutions. And when it comes to an initial value problem, they're going to be identical. They're going to have to be identical, with the exception of maybe, like if it's got sine and cosines, maybe you're using some sort of an identity to combine them or something like that. But barring that, no, they're all going to work out, because they're going to, I mean, the only thing we might do is come up with a different fundamental set of solutions. But yours and can be written as a linear combination of mine and vice versa. Right. So just like when you were told to find a basis for a space, there wasn't necessarily just one basis that worked, but every basis could be written in terms of the other basis. Same deal here.
That's wild.
It is.
That the two are totally unrelated, yet they're not unrelated at all.
Yes, I agree. And to me, that's the beauty of math, how everything gets intertwined. So, but we'll save that more for next time. The other thing I do want to remind you, though, because it is this week, our first exam is on Friday. So I don't want you to get blindsided by it. You're probably already that was probably enough of a blindside when you're like, wait, what? So our first exam is on Friday, and it's going to go through chapter 4. So chapters 1 through 4 for the exam on Friday. But we'll talk a little bit more about that on Wednesday as well. But I just wanted to give you that heads up so you can start preparing and you can start thinking up questions to ask me on Wednesday. All right. So other than that, don't forget to get in there and finish the homeworks for tonight. Do it midnight. But other than that, you guys have an awesome couple days, and I will see you when I see you.